The artificial intelligence revolution has been strictly confined to the digital realm. It excels at knowledge work, text generation, and digital media, but it operates entirely behind a screen. That digital-only AI economy represents a tiny fraction of global GDP. The horizon is the $100 trillion economy of atoms, agriculture, manufacturing, and transportation. Automating this infrastructure requires physical AI, intelligence designed to interact directly with the physical world through robotics. Industry leaders are already pivoting. Initiatives like NVIDIA's Omniverse and their physical AI showcases make it clear that the focus is shifting from generating text to moving machinery. But progress is stalling against a severe engineering bottleneck. The data pipelines and educational frameworks we built for digital AI cannot simply be copy-pasted into the physical world. The methodologies used to ignite the linguistic AI revolution lack the mathematical and physical architecture to scale to the robotics revolution. Making this transition requires abandoning the standard AI data pipeline entirely in favor of a completely new architectural flow. The existing digital architecture funnels simple web scraping into data cleaning, which outputs to a large language model. Compare that to the physical pipeline. Procedural 3D simulation creates synthetic data, feeding into a world foundation model and ending in edge inference. To realize the vision of autonomous infrastructure, engineering must step away from pure software paradigms. This architectural shift requires an immediate change in technical training. Professionals must move beyond digital collection and learn to master the generation of virtual training grounds. Let's zoom in on the model phase of these two pipelines to see exactly how they process reality differently. Large language models operate strictly on linguistic probabilities, parsing massive text-based matrices to predict the next word in a sequence. Robotics requires a different engine, world foundation models. This comparison illustrates the difference. On the left, a text-based network. On the right, a world foundation model, natively processing physics, spatial dynamics, kinematics, and thermodynamics. Academic institutions must pivot their curricula accordingly. The heavy emphasis on natural language processing needs to give way to courses in spatial AI and video predictive modeling. Training a neural network to predict the exact physical sequence of a glass falling off a table requires different mathematics than predicting the end of a sentence. The era of computer science existing in a software-only silo is over. Physical robotics shatters the traditional boundaries of the discipline. This diagram shows the interconnected system required to deploy physical AI. It relies on 3 separate computers working in unison, starting with a training supercomputer that feeds data directly into a simulation environment. The supercomputer does the heavy lifting of training the model, while the simulation environment acts as a hyper-realistic digital twin to test those models safely. The crucial third component is the edge computer, which runs the localized inferencing physically inside the moving robot itself. Operating this triad demands deep interdisciplinary systems thinking, forcing a merger between mechatronics, mechanical engineering, and software engineering. Engineers must understand exactly how a single microsecond of network latency in the software translates directly into a physical miscalculation and collision by the edge robot. Modern engineering education must produce polymaths who grasp the direct physical link between abstract code and atom manipulation. That physical link elevates safety engineering from a secondary concern to the primary focus of model deployment. When a digital model hallucinates, it generates bad text. When a physical model hallucinates, the result is catastrophic physical damage. This creates the core friction point stalling the robotics industry. An AI model can perform flawlessly in a digital environment, yet fail completely when transferred into a physical body. Engineers call this drift the simulation to reality, or sim-to-real gap. This split screen demonstrates the gap. The perfect execution on the left degrades on the right due to unmodeled variables, microfriction, sensor noise, or unexpected lighting variance that the simulation failed to capture. To solve this, hardware-in-the-loop simulation and rigorous physical safety protocols must move to the absolute core of AI education. Without intense edge case testing, we cannot safely cross the barrier from simulation to reality, leaving any physical infrastructure we automate vulnerable. Addressing those edge cases brings us to the data pipeline phase, where we determine how these advanced physical models actually acquire their training data. The traditional data science model relies on gathering, cleaning, and labeling real-world data from the field. That model is obsolete in robotics. Gathering physical data for every possible edge case, like a self-driving car encountering a moose on a dark, snow-covered highway, presents a physical impossibility. Collecting millions of real-world iterations of rare, dangerous events is financially and practically unfeasible. The solution to this bottleneck is synthetic data generation. This chart shows the exponential difference in volume. Procedural generation engines rapidly iterate thousands of synthetic variations of a single event across different weather conditions and variables, a process known as domain randomization. Universities must aggressively teach digital twin architecture, instructing students on how to build these scenarios using formats like universal scene description. This establishes a new priority. Compute has become the data. Simulation provides the infinite breadth of experiences that are physically and financially impossible to gather in reality. But relying on simulation exposes the final bottleneck in the pipeline, the massive human labor required to manually build hyper-realistic 3D environments. Historically, creating a physics-accurate virtual factory required a rare, highly specialized blend of 3D modeling and software engineering. Now, agentic AI models are automating the construction of these complex virtual worlds, snapping steel beams and conveyor belts into place without human hands. This shifts the role of the human engineer from a manual builder of physics engines to an orchestrator of AI agents. The required skill set is evolving. Engineers must prompt AI agents, supervise their autonomous generation, and critically evaluate the physical accuracy. Teaching a student how to manually program a physics engine is rapidly becoming obsolete. The modern curriculum must focus on collaborative, agentic workflows. Looking at the full physical AI pipeline, we can see the complete scope of the engineering reality. It requires a deep overlap of mechatronics, 3D orchestration, and safety engineering. We are developing the ability to manufacture specific knowledge and embed it into machines capable of building, healing, and harvesting autonomously. The limitation to achieving automated gigafactories and autonomous infrastructure is no longer computing power or hardware capability. The stalling point is strictly a human expertise bottleneck. Modern education must aggressively break down the legacy silos separating computer science, mechanical engineering, and the physical sciences. We must teach the next generation how to code the minds of machines, while simultaneously training them to construct the virtual worlds where those minds learn. Only then can we safely bring them into our physical reality.